Welcome to episode 4 of Bit by Bit, where I explore low-level programming on the Apple IIe. Let's just dive right in. So we're looking at the assembly lines of the book. We're in chapter 4, where we talk about loops and counters. This was written in the January 81 issue of Soft Talk magazine by the author. But let's kind of, we'll look at what he's written, and then we'll kind of parse it out. So basically, he's going to start off by talking about binary and hex. He's going to do a pretty deep dive into binary. I'm going to talk about the status register. We'll look at this. This is the breakout of the bits of the status register. And then he talks about incrementing and decrementing the registers or memory location, and we'll kind of parse that. And then he gives us an example, and he gives us a basic example followed by an assembly example. And that's pretty much it. All right. So what does it look like for us? Well, let's talk about what we know so far. So what I covered in the first three videos are the different basics, the floating point basic and the integer basic, the machine monitor and the machine language monitor, the mini assembler, Merlin, and some opcodes, specifically these opcodes. So JSR to an address, I guess we'll need the ADVR, JSR, RTS, which is the return from subroutine, and then a couple of, or three, instructions to load either the accumulator or the X register or the Y register with a value, either an immediate value or from a memory location. The store to the accumulator, store what's in the accumulator to memory location, store what's in X, store what's in Y. So these are all the things that we know assembly-wise by reading the first three chapters of the book. What we're going to cover here, though, is we're going to look at process of status flags, and we're going to learn some new opcodes, specifically the increment X, the increment the value that's in the X register, the increment the value that's in the Y register, decrement what's in X, decrement what's in Y, increment some memory location, or decrement some memory location. What's missing, you notice, is that there is no increment the A register, the accumulator. You can't do that, and so there's no instruction for it. We're also going to cover the branch not equal opcode, which is the first flow control kind of opcode that we're learning. And that's at a high level what we're going to cover. So let's just jump right in. So when we're talking about looping, which is the topic of the chapter, and I'll leave the binary discussion and the hex discussion. You can go read about it. We've talked about it a little bit in the previous videos, and I'm not sure it's terribly relevant at this point, other than as background. So let's just talk about looping. When we're looping in any language, we're going to do four things. We're going to initialize some control variable that's going to be like, when are we done? Then we're going to do some work, an iteration of the work, a piece of it. And then we'll increment the control, meaning that we'll head it towards the finish. So if there were 5 things to process, after we've done one, there'll be 4 things left to process, 3 things left to process, and each time we'll get closer to done. And that's, the loop is way more flexible than that, but that's the gist of it. And then after we've incremented, we can test to see if we're done yet. Now, the order of these operations can vary. I tried to tailor it towards the examples he gives. In most of my looping, what I do is I do an initialization, I test immediately, then I do some work, and then I do the increment at the end. And that's kind of how for loops work. But anyhow, be that as it may, we're going to do these 4 things every time we do a loop. And so I'll cover that as we go. And let's get into the book example right away. So I'm going to start up the emulator. I'm going to boot off of DOS disk or whatnot. It boots, oh, that's the Merlin disk. Hang on, get the DOS disk. DOS. All right, we're in DOS. Now we have access to both basics. I'm going to type in this program right here. We'll clear the screen just to get started. Make sure we don't have anything in memory. Okay, fine. our program is going to clear the screen. It's going to call the home routine, which puts the cursor in the top left and blanks it out. And then our second line is going to set the control variable to initialize it to some value. In this case, we're going to set it to the end value. We're going to count backwards. So we're going to start at 255 decimal. And then we're going to do some work, which is print the x value. All right, so we've initialized, we've done some work. Next, we're going to increment. So on 40, we're going to set x equal to, we're incrementing backwards because we're starting at the top at 255 and counting down to 0. So we're going to do our increment, which is really a decrement, but it's an increment with a negative value. We got x equal x minus 1. So after the first time it was 255, now it gets here and it says, you're going to make this 254, and that'll be the value going into line 50. At line 50, we're going to say if x is not equal to 0, we're not done yet, then just keep doing it. Go to 30. We won't go back to 20 because if we reinitialize the 255, we would never end, right? So this is that. And then 60, we just say end for completeness, and we list it out. And that looks pretty much like what they did, but let's run it and see what happens. 255, now works its way down. It's kind of slow, it's basic, so it's going to be interpreted. The machine itself, Apple IIe, has to go through a lot of hoops to get this to do its thing. A lot of machine instructions being being run, and so it takes. But it counted down from 255 down to 1, and didn't print out 0, which we can think about it. Let's see, it starts off at 255, prints it out. It did. It subtracts 1 and it's 254, and it says, is that 0 or is that not 0? If it's not, just go back to 30. So it goes back and it prints 254, then 253. And it gets down to the 1, or even let's start at 2. So let's say x is 2. If 2 is not equal to 0, then go to 30. Okay, it prints 2. Then it subtracts 1 and it's 1. And it says if it's not 0, go to 30. And it prints out the 1. And then it gets down and it's 0, and it says if 0 is not 0, then go to 30. Well, it doesn't do that. So that's why it doesn't print out the 0, because of the way we wrote the loop. If we wanted 0 to print, we'd have to change the logic and say, oh my, if x greater than -1 or something like that, go to 30. But that's kind of how it works. So let's look at the list again. That's a basic loop. At line 10, we just clear the screen, but line 20 is the init part of the loop. The print x is the work part. The x equal x minus 1 is the increment, and the test is if x is not 0, then go to 30. And I'm going to explain why there's spaces in there on 50, but they're just there. Don't hurt anything. Seem to work. Okay, let's do assembly. So we're going to kick the DOS disk. And we're going to get the Merlin assembler loaded back up. And we've got Merlin work on there already, so we should be good. Reboot the computer. And it loads up Merlin. Since we're going to type in some Merlin, this looks like it's going to be a pretty short video. Hope that's okay. We're going to go in and we're going to edit our code in Merlin. We're still using the line-based version. So we go into A for add, and it starts at line 1. May as well have a comment. So Control P, enter, space, Control P. And then we'll call this, looper. All right, and we can have an empty line. And then we can do space, obj, $300. That tells it, go ahead and put this into memory at 300. And it's required until we get to the other full screen assembler, but at this point we need it. And then we can set the origin also to 300 because that's where our program starts. And then we can create a label called home, which homes the screen, and then space, and then EQU, which sets it equal to this value. What value? FC58. FC58, which is another routine we didn't write that they wrote in the monitor that we're calling. So we're going to leverage some code that we didn't write, and it's going to clear our screen for us. So done. All right, and then we'll leave a blank line just like in the book, and then we'll create another label, and I could call it start. I could call it init. That would be kind of it too, but we're going to start JSR home, which is just home. The HOME here on line 9, it's expanded to $FC58. We could have just typed JSR $FC58, but we might want to do it more than once. So this gives us a nice abbreviation for it. So there's start. And then we're going to do our first kind of use of these new opcodes that we're learning about. And we'll kind of, we'll talk about them a little more here in a minute after we see it work. And then there's an immediate value. That's what the pound means. And it's an X value. That's what the dollar means. We're going to load the X register with FF, which is hex 255. And how do we know that? Well, we go to a calculator, and if we don't remember, we make sure we're on hexadecimal and type FF, and it tells us it's 255. All right, which is initializes, puts in the index register the hex representation of 255, which is the top of where we want to start, and we're going to count down from there. So we're going to start it there. That's the init. And then and then we're going to go to, we're going to start the loop. So once it's been initialized, we can store that value in a location. We're going to take the value that's in X, which is 255, the FF to start with, and we're going to poke it into address 700, $700. And it doesn't have the pound sign because it's not an immediate value. It's that's an address. And that's going to store whatever's in register X into location 700, which 700, if you kind of dig back into the back of the book, there's a section there called, I'm going to show you. There's a show that looks something like that, which is the screen. Hopefully you can see that. But even if you can't, just take my word for it. 700 is a location on the screen, and we'll figure out where that location is, somewhere on the left-hand top side when we run it. And then the next thing we're going to do is decrement X, which just subtracts 1 from whatever's in register X. So if it's FF right now, which is 255, it'll become 254, which is FE, and then FD, and then FC, and then FB, and then FA, and then F9. 8, 7, 6, 5, 4, 3, 2, 1, 0, and then it's E, F, and so on and so forth. So decrement X. That's a good one. And then once we've done that, and that's the increment, it's negative. And then we're going to have our test. And our test here is using the BNE instruction, and we're going to BNE to the loop, which again is just whatever address this line is on, whatever address loop compiles into, where when we look at it in the machine monitor, we'll loop for this STX. Whatever address that is where this is going to jump to every time that this evaluates to true. So it's going to branch not equal. And we haven't really talked about the status flag yet, but we will in a minute. All right, so it's going to branch as long as the result of the comparison, which is, how do I say it? The decrement operator, the result of the decrement operator. It's going to take 1 off of what's in the X register, and that's going to count down to 0. Once it reaches 0, it's going to set a flag that when we say branch not equal, it's going to say, oh, it's 0, so I don't branch. Whereas every other time I'm going to branch. So when it's FF, it's not equal, it's not 0, it's going to branch to loop. But when it gets to 0, it's going to not branch, and that's going to be the end of it. So it's going to go to the end, and that's going to RTS. And that's going to be our program. Let's list it, make sure it looks okay. We'll assemble it, make sure it assembles. No, we don't need to update, we just wrote it. It assembles, and there were no errors, and it assembled 212 bytes, and we can kind of see what's going on. But now we can see that this list thing's kind of getting annoying because we don't, even though we do care about the address things we're at, we want to see the rest of that code. So let's take a look at the code again. There it is. Let's go ahead and append some more code to the end. So the code I want to do is I want to tell it not to list, which is LST off. Okay, let's list it. Let's assemble it, update it, and then we get just the code. And now we can see all of our bytes and everything without the distraction of the symbol list. Later, if we want the symbols back, we can change it. But here's the code. What it looks like is at 300, we get 20, which is our JSR, and then to FC58 is the address it's going to jump to. They're in reverse order in the listing, but you can see it over there, JSR home. And once it's done the JSR home, it comes back and it does A2FF, which is LDX, loads the X register with the immediate value, the FF, and that's where it starts. Then it does a loop, which is 80, and a store X, which takes what's in the X register and stores it at location 700. And then 308, CA, whatever the heck that is, decrement X, it's gonna decrement X, and that'll count down to 0, and it'll keep looping until it's 0. And that's what those other bytes mean. And there are 12 bytes, and that's it. Let's exit the editor because it compiled okay. We'll exit the editor. We will save the source. We will call it looper. We'll also save the object code. And looper's fine. We'll say yes. Of course, I just saved it on drive 1. Oops. All right. We're going to change the drive 2 and do the same thing. Looper, we're going to say yes. And you'll probably run out of space if you aren't careful over there on drive 1, which is fine because you made a backup anyway. But object looper, yes. Okay. Now we're going to quit Merlin and go to the regular DOS prompt here. We could get back with ASSAM, but for now, let's just do a catalog and see what we got. There we go. We got the test bell from last time, play regs from last time, test bell from the time before, and looper. We can run looper. And that's kind of funny because, okay, let's, it runs so fast we can't even see it because it's running in machine code and it's just that fast. But here's what it's doing is it's changing the value of this cell right here. And that's where 700 is on the screen, if you're wondering. Okay. 701 would probably be the next one over, and the next one that I can't remember. But this is it. And it replaced it. It counted down from 255 to 0, 1 really. And this here, the inverse A, is the last one it printed. It printed all both bunch. We just didn't see it go. And it ended on this note. And the book tells you, oh, turn on beeps and you'll be able to hear it. But we don't know. Let's see, what else? Yeah, brun, we'll run it again. Brun looper. And we'll pay close attention to that A. So fast, can't even see it. Do we believe that? Maybe. Let's go back in here. We're in drive 2. Let's we have source loaded, so let's just go to the editor and let's list it. Man, 255 to 1. I don't know, man. It's all the way down to 1. I'm tempted to just edit line 11 and do the beep thing. Okay. Yeah, let's do that. That's annoying and it'll sound horrible, but we'll do it anyway. Let's see. We want to edit 11. All right, instead of looping, well, looping's fine. Loop. Instead of store X, we're going to call JSR. And then if we had bell, if we had an EQU for bell, we could do that, but we're just going to type FBDD. All right. Yep, seems reasonable. Let's list it. And this is what the book suggests anyway, and I don't know a better way. So it's going to start and it's going to loop. It's going to, on each iteration, it's going to beep and then decrement, test it, go through it again and again. And yeah, this seems right. Okay, so let's assemble it. No, we don't need to update source. 12 bytes, 0 errors, and there's my JSR FBDD, so it seems like it's going to work okay. Let's quit the editor. We won't save this one. Let's see, what do we want to do? It created the object code. Can we run it from here? Oh, I guess we'll have to save it. So we're going to save source, and no, we're not going to call it looper. We're going to call it looper2. And we'll save the object code as well. Looper2, yes. All right, we'll quit, and we'll run looper2. That's a lot of beeps. Still beeping. Still beeping. Wow, that's a lot of beeps. Okay, very good. If you want to play with the beeping thing, maybe change that from 255. So let's do that. Let's go back into the assembler. Let's go back into edit our source code. Let's list it. And where it says 255 there on line 10, we'll change that to 10. Okay, so we're going to edit line 10. And we're going to go, yeah, LDX is fine. And then it's an immediate, it's an immediate value, it's X. And we'll just go with 10, but we'll go with 10 with 0 8. Okay, that's hex for 10. Let's list it, make sure it still looks okay. Yeah, this time it's going to beep 10 times. I think we can handle that. Let's see, do we need to make any changes? Oh, we're going to assemble it. We don't need to update it. That assembles, no errors. We'll quit. We'll save it. Looper2 is fine, so yes. And then object code, we'll save that too. Yes. We'll quit, and we will run looper2. B run looper2. 10. Much more reasonable. Sorry about that. I didn't know how long 255 was, but it's very long. Okay, but there we get to see it working. Whereas with the printout, it was so fast you couldn't even see it. The reason the beeps, by the way, the reason the beeps, the 255, the reason that's okay is because those are like a second, there's a delay between them, and there's a time that they take to do. So that's why they seem to take a while, because there's like 255 times. But they're, if they weren't constrained by their own timing, okay, they would go by instantly too. All right, because machine language is very fast. Basic is very slow. So hopefully that was interesting there. Let's what did I jump past some things? So let me get back into the assembler. Okay, we'll edit, we'll list. And there, okay, we got that word, all those instructions and stuff. Okay, yeah, good. Yes, let's take a look at the book. And we'll go to the end of the book down here. Let's see. Yeah. Okay, there we go. Yeah, we'll start here. Okay, so we're using load X. We could have used load Y. We could use load A, but then we can't decrement it or increment it, so that's pointless. We'll leave the accumulator alone for these things. Oh, yeah, that was the other thing. Before we jump into that, let's cover the status register. So here's our programming model. We're using the X register, this one here, 8 bits. We can increment and decrement the index registers, so we can use either one. We can't really use the accumulator for this sort of thing. And we're not talking about these two, the program setter and stack pointer. But we are going to talk about this process status register. So I'm going to move this over a bit. There we go. And we'll create a new little doc, and we'll start looking at this. So if there's 8 bits in the world, let's see, we'll just put 1, 1, 1, 1, 1, 1. There's 8 bits, okay? And you can think of these as light switches, okay? Like there's a light switch turned off. There's a light switch turned off. There's a light switch turned off. Okay, and we can kind of look at them as a set of switches. They could be banked up the other way, okay, like this. We can do that. It doesn't really matter. For our intents and purposes, all we're interested in is the fact that there's some switches. And when they're 1, they're on. When they're 0, they're off. And and there's 8 of them. And we're going to ignore this one here, okay? This one doesn't matter. But the others matter. These 2 matter, and these 5 matter, okay? But we can split them up like this because then we can talk about them as if they were hex values, like this one, which is, remember, this 4th bit to the left is 8, and this is a 4, and this is a 2, and this is a 1. So 8 and 2 is 10, which is A, right? And then there's another one over here. And this one's got an 8 and a 2 and a 1, so that's 11, which is A, B. Okay? And that's if we were looking at in terms of hex. It just gives a convenient way to see at a glance what the values are. Now, each individual light switch controls something different. In this case, we're looking at over here, this first position, this first switch is the carry switch. If it's a 1, there was a carry in some math operation, like you added a number to a number and you had to carry the result. Okay, this would be 1. If it was 0, there would be no carry. All right, and then there's a 0 flag. There's an interrupt disable flag and that kind of thing. And when we don't care about the value, we can put dashes just to help us keep track. And then the break command, we don't care about that one, but we do care about the 0 flag in what we're doing here. And then we also care about, that was decimal mode. That's the break. Again, this one is not used and not used. And then this is overflow. And this one is the negative sign. Okay. We care about these 2 bits when we're talking about this operation. And the way we know that is when we load the accumulator, it affects the negative flag and the 0 flag. Okay, those 2 flags matter in the context of loading the accumulator. Now, when we decrement the accumulator or increment it, it also affects the negative flag and the 0 flag. And honest to God, we're not even going to care about the negative flag right now. We're just going to look at the 0 flag. Well, the reason for that is because when we do the branch not equal, the BNE, wherever it is, branch not equal, it's going to branch relative to the 0 flag. Okay? And when the 0 flag is 0, or when the 0 flag is not 0, then it's going to go to the location we tell it to. Otherwise, it's going to drop through to the next instruction. So that's kind of a bit about the processor status flags. These guys. Okay, so we don't care about negative. We don't care about overflow right now. This isn't even used. The break command, we don't care. We don't care about the decimal status. We don't care about the interrupts. We do care about 0. We don't care about carry. So we're looking for this bit, which is going to be interesting to see how we figure that out. And we're not going to care about this. So that's the one we're looking for. All right. Now let's start with the loading of the register. There it is. Okay, so we're going to load X. That is what I said. Yeah, load X. Yeah, load X. Okay, and we're loading X with an immediate value. So we look in here, we go, oh, the immediate value. And then that's going to be pound dollar, and then the actual value we want to do. Its opcode is A2. All right, and we can see that when we do the assembly. No, we don't need that. When we do the assembly, we can see that A2 is this guy right here. Okay, load X, A2, and then the immediate value is the A2 0A. So that's the byte that gets stored, 2 bytes. When it happens, when we step through, when we load the register with the 0A, it's going to cause the flags to be set. Okay, and we should probably play with that. So let's just bail on all this. We can quit here. Yeah. Okay. And then to get into the monitor, nah, I don't think so. Let's we've saved our code. Yeah, we have. So I'm gonna boot the well, actually I'm just gonna reload this. So let's load it with the DOS disk, the DOS master disk. Okay, we don't care about what's loaded there. We'll reboot. Control F2. No, we don't need that. We just wait. So here we are on the basic monitor. We want to get into integer basic because we're going to use maybe the mini assembler. So, but we'll start with the call to -151. And I've kind of glossed this over a bit, but let's look at this in the calculator. So I'm going to set the decimal mode, and I'm going to type -151. Okay, that's a big number, very confusing, not particularly helpful. All right, but if I told you that the space, that the amount of memory that we have in our extended 2e is kind of 2 to the 64th, which is, 2 to the 16th power. We have 16 bits for each address, which gives us access to 64K of RAM, which is equal to 65,536, which happens to be equal to 10,000 hex. That's a lot to keep track of, right? 16 bits in the address means that we have this many addresses, 65,000, which is what we call 64K. And then that maps to this nice round, super round number, 10,000 F. Okay. This many addresses mean we have access to 0, 1, 2, 3, 4, 5, all the way up to 65,535, right? So it's really the last address we have access to is this -1, okay? And we see that that's a nice round number too. That's FFFF. And that fits within our 2 bytes for the high orders, and two nibbles, a byte for the high order and a byte for the low order. Okay, so FF and FF, which is kind of like the space we're operating in on the Apple IIe. But we're working in decimal, so this is the last address. What if we subtracted 151 from that? All right, well, probably no need. If we subtracted 1 from 2 to the 16th minus 1. If we did that, 65,535. That's exactly what we just did a second ago. So painful. So 2 to the 16th minus 151. That's the math we're looking for. FF69. That should be familiar. Like, wait a minute, FF69, that's the address of the monitor. And it sure is. And it's just that 151 apparently is easier for folks to remember than 65,385, okay, which is the actual decimal equivalent of FF69. But this gets us there as well. Who came up with this? I don't know. But when you see negative numbers in BASIC and you see call negative something or other, it's from 2 to the 16th. So 2 to the 16th minus 151 is equal to this, which in hex terms, FF, way easy to remember, FF69, which is the monitor. So we're going to call into the monitor, and there it is, which is the same as if we were in the monitor or somewhere else, and we typed FF69, go. That's the exact same thing. They both enter the exact same code. All right, so there's that. Wow, that was a bit of a mouthful. Apologize for any confusion I caused along the way. Hopefully it's been straightened out. So but anyway, we're in the monitor, and we're wanting to explore what load X register does. Remember that you can see the status of the registers with Control E and enter. Let's load a value into X, and we know how to do that. So let's list 300. We'll put our program there, and there's nothing in there yet. So we're going to take 300. We're going to do LDX, which is A2. We're going to do an immediate value. We need an opcode of A2. So we're going to put A2, and then the value we want in there, which is, let's just stick to the easy stuff. Let's do 22. Okay, and then we'll break. So we're going to run this code. So let's disassemble it and take a look. So right now we've done LDX, immediate value of 22, and then we're going to break. Let's run it. Let's remind ourselves what the registers have in them. All right, X has 24, the S thing has 10. We're going to execute our code, 300G. Because it broke, it shows us the contents of the registers. And so what we have is the accumulator, we don't care, but we have the X register that we changed. It put the 22 in here. We didn't change the Y, but the processor flags are set to 30. And that means 30, which looks like this. This is 0, obviously a bunch of zeros, and this is 3 over here. And the only one we're really looking for is that one. That's the 0 flag, okay? And it's 0. So it's not 0. It's not set. If it was 1, that would be if we loaded a 0 into register X. So let's take a look at our code again, and we'll make a little change, and we'll see it in action. Here's the LDX 22, which is A222. We're going to change it. We're going to go 300. We're going to go A2, and we're going to add 0, 0. That's a 0. All right, and another 0, 0 with that. Okay, and we'll list it, see what's going on there. And we can tell those zeros are different. Okay, this 0, 0 is expected as part of this command. So it gets compiled in, assembled in the LDX immediate value of 0, 0. Whereas this 0, 0 is not part of that command, and it's its own command, and it's a break. So now we can run it again, but let's check registers before we do. All right, there they are. Processor flag it's still 30, which is the 0 flag is not set. Let's run 300G. Okay, now we see it, and we see that it's 32. Well, that becomes 32, and that means that guy is on. Okay, 32. So it's 0. And it's 0 because we put 0 in the register. And that register and that operation, LDX, causes the flags to be set. So it's like, okay, I loaded the register and it was 0. And it gets put in there, and there it is in the processor flags. Yippee-ki-yay. Good stuff. Sorry about any confusion I might have caused along the way. All right. Oh, more of the book. Okay. So that was the easy way of getting it into the X register. We loaded it immediately. There it is. We could have gotten it from an absolute address. We could do that. That would be kind of take a little longer, but let's not do it now, but we could. Anyway, we loaded it into the register, and when we did, it set the 0 flag when it was 0, and it cleared it, set it to 0 when it wasn't. Now we want to try we want to see what happens when we do decrement. Okay, well, right now it's at 0, so let's not do that. Let's take a look at what we got. Okay, fine. We got LDX with a 0, but let's put 2 in there. So we're going to re-edit it. 300, oops, sorry, 300, A2, and then we're going to put 0, 2. 0. Okay, 300L. Okay, we look at the registers before, oh, I must have mistyped. 300, all in A2. Yes, okay, now it's working. So let's look at the registers, make sure that we're still kind of in a good place. 32 is still there because it's still, the last time it did an instruction was load X, and it was 0 at that time, right? But now we're going to run it. And when we run it, this time we're loading in 2, so it should go back to not 32. Let's run it and see what happens. And sure enough, it's back to 30, but we only care about this second bite, second nibble, and really if it's 2. So it's not, which because we put 2 in there, it's not 0. That makes perfect logical sense. But now let's try the decrement stuff. And to do that, we're going to look at the decrement instruction in our list. And it's going to say decrement X by 1, takes X minus 1 and puts it in X. It's an implied instruction. It doesn't take any arguments. And its opcode is, mnemonic is DEX, and its opcode is CA. So all we got to do is put CA somewhere. So let's take a look at our code, and we'll just put it right after this. So we loaded it with X. Let's decrement it at line 302. So I'm going to put 302, and I'm going to put, what is it, CA. That'll decrement it. So it should become 1. And then we'll list it, and you can see what the effect of all this typing does. All right, which does loads it with 2 and then decrements it and then stops. So we take a look at our registers before we run. we see that the processor flags don't show a 0 flag because that second nibble is 0. And X has got 2 in it. Let's run the code. It does it again, and then it decrements it by 1. So X is now 1, and the processor flag, I'm sorry, the status flag is still 0. So a 1 is not a 0, right? And then we can look at again, and we'll put in 303, we'll put a CA as well. So 2 decrements, right? Which should get us to 0, right? And then it'll stop. So 300L, 300G. And you can see that the 0 flag got set. So it's working like it ought to. The decrement operation, the decrement X, affects the 0 flag and the negative flag, but we're not looking at that just now. But let's decrement it one more time at line 304, address 304. We'll put a CA. And that'll take us kind of below 0, whatever that means. Let's take a look at the code. All right, yep, 3 decrements. We only had 2 to use, so let's see what the effect is. Is it going to break? Not really. But it is going to change the way things work. Okay, so it's not 0 anymore. X is set to FF. So apparently the counter is some kind of a loop, like a mileage gauge, that goes 2, 1, 0, and then what's the last number it knows about? FF, and then FE, and then so on and so forth. So that's a bit about that decrement stuff. A little more detail, right, based on what we read here. Let's do something in memory. So I'm going to we're going to store a counter over here at 310, which we can't see right now. Oh, there it is, 310. We'll put a value there, and we'll start it at 20. Okay, so I'm going to poke 310, and I'm going to put 20 in there. And then we'll list it and make sure it got there. Okay, and now we're going to programmatically, I'm going to erase all that starting program there. We're going to programmatically bump it by 1 using the increment operator. And the increment operator, that's this guy, INC, it takes various incantations, but one of them is called absolute. And that's the one where we give it an address. And we'll give it this address 310. And we'll use this EE thing to do it. Bump it by 1. And we'll do it a couple times to see what the effect is on our memory. Which by now you're like, this is boring, because whatever you type is what it's going to do. But it's still kind of fun. So let's see, 300 colon, and I'm going to 0 out that memory. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. All right, and then we'll list it. Make sure it's all right. Yeah, but our 20 is still sitting out here at 310, which we're going to bump it by 1. 320, it'll be 21. Bump it again, it'll be 22. So at 300. We're going to put in a new instruction. We're going to see. I think what we'll do is we'll load it. No, it's already loaded. We're just going to increment. So here it is, increment. We need to give it EE is the opcode. And then we have to tell it the address that we want to mess with. And the address we want to mess with is 310, but we have to give it in the least significant byte, the 10, and followed by the most significant byte, 3. All right, but we're going to do it twice. So EE 1003, same address. We're going to bump it twice, and then we'll kind of break. So let's see what that looks like in assembly language. And it looks like we're incrementing 310, and we're incrementing 310, and we're stopping. 310 is currently 20. Let's run it and see what happens. Right? First off, before we even do that, we get this, there's no 0 flag, whatever that means. So the increment flag, the increment operator also affects the 0 flag. So if we incremented the value at 310 and it became 0, this would be set to 2, and it'd be 32 at that time, right? Because this would be 0, but it's not, because it's 21, then it's 22. It's never going to be 0 if we keep incrementing until we go to FF, and then it rolls around. But here it is, we got it running. Let's see. Oh, we need to look and see what the actual memory is. And let's just do it this way, 310, 22, 20. It was 20, then it was 21, then it was 22. Let's do this. Let's decrement a couple of times. Okay, so we're going to change this program so that it decrements this address twice. So all I'm going to do is change EE to whatever decrement is. So I look around and I go, where's decrement? There it is. And I look for the absolute one, and it's called CE. So I'm going to change this to CE, that to CE, and then I'll rerun it, and it should go back to 20. Let's try it. 300, 300 colon, and we'll go CE, and then we'll go 303, CE, and then we'll list it. Okay, a couple of decrements now. That's all good, and it's 22. So it should go back to being 20 after I run it. 300G. Okay, we noticed that it's definitely not a 0, okay, at that location, because that's what that means. The decrement also has, if you look, also has an effect on the 0 flag. All right, so there it is, 300G. We rate it. Oh, we need to look at it. 300, 310, and we don't need the L. 20. It's back to 20. Let's put 2 into it, and we'll decrement it twice and see what happens. All right, so we're going to say 310. We're going to put 2 in there. So we look at it and make sure we got a 2 in there, yeah. And then let's list our program again and just see what it's going to do. It's going to decrement it twice. So the first time it decrements is going to be 1. Second time it decrements is going to be 0. So that processor flag should get set. Let's see what happens. There it is. Yep, the 0 flag got set. That's what the 2 means here. And we got to look at 310 to see what it is, but it's 0. There it is, it's 0. We could run it again. So before we do any more, because it's still 0 right now. So when it decrements it 2 more times, it's going to go FF, FE. That's our theory. Let's test our theory. And let's look at 310. And there it is, FE, decremented twice. So I think that covers it. Let's see if there's anything else I needed to talk about in this video. I don't think so. I think that'll do it. All right, hope this is helpful. Thanks for watching.